if we have a large energy gap between states, okay, it's logical that the higher energy states will be even less populated, right, by molecules in the systems than if the energy levels are really close together, right? So getting from one translational state to the next or one rotational state to the next, those are smaller energy gaps than, say, a whole electron shell change. Okay, these electronic gaps are really big. The system needs thermal energy to reach higher energy states. Okay? So at a higher temperature, the higher energy states become more populated. So this term here is called Boltzmann factor. Recall that EXP is our notation for E raised to the. Like I said, it is an exponentially decaying function, so that's why we have our negative sign here. Here's our exponential function. Here's the negative sign for decay. U sub j would be the energy of the jth level. Okay. Kb is just Boltzmann's constant. And T is also temperature. Okay. So you can calculate a distribution at a given temp. And if you change temp, you have to look at the distribution again. Because as you have higher and higher temperatures, things can start to get into higher energy states that they couldn't before.
So is the T on the numerator or denominator?
The T is in the bottom. This is a negative U divided by KBT is the bottom term. Yep. What are the units of Boltzmann factor? There are none. That is correct. What are the units of, say, U? Joules. What are the units of KB? And we're multiplying joules over Kelvin by Kelvin, okay, on the bottom. So we get the temp to drop out, and then joules over joules drops out, and it is unitless. What happens to Boltzmann factor as U goes up? As U gets bigger and bigger, so the energy levels get bigger and bigger, what's happening to that whole term, Boltzmann factor? It's getting smaller and smaller, right? Because this is a negative. Okay? So this negative number here, so E raised to a bigger negative number is going to be a smaller thing. Okay? What happens to Boltzmann factor as temperature increases? It gets bigger, okay? So as U goes up, it gets smaller. As T goes up, this whole term, okay, as T gets bigger, U over KBT gets smaller, but it's a negative, so it is a smaller negative number, okay? It's getting less negative, if you will. The whole term gets bigger, okay? So as energy goes up, it's harder to get into bigger levels. As temperature goes up, it gets easier, okay, to move up into higher levels. And this whole term is unitless. The number of molecules N at a particular energy level decreases exponentially with energy U of that level, okay? And that's what's being shown here, okay? So you have really big energy gaps. Okay? These are all just considered some energy times KBT. From 0 to 2 and 2 to 4, you have most of the molecules in the lowest energy level. And as the gaps get a little bit smaller, now you have 1, 2, 3, and 4, or now these are all half spacing. You see more and more molecules populating higher levels. Energy levels are like stairs, though very rarely are they ever regularly spaced like this. Okay, you'll just be given values for the energies to use, and they won't necessarily be evenly spaced. Okay, but as the steps were to become smaller, smaller delta U, the higher energy states get more populated. So the number of molecules in a given state is related to the energy of that state, sort of by this definition here. So you can look at this top term. This is Boltzmann factor, right? Now EXP is written as E to the, and this whole term's on the bottom, remember. So if I want to look at sort of the ratio of molecules in the second level versus the first, I can divide these two things, and I'll be able to simplify this to the difference in energy between the two. And so as this value gets smaller and smaller, this value over here is going to get bigger and bigger. So even if you don't know all the energy levels, you could still think about the relative number of molecules that would want to be in a given energy state, okay? If you can keep your even spacing assumption. This sort of falls apart if they're no longer evenly spaced. There's an error in the figure in your textbook that I want to point out. So here it's showing increasing temperature. It has low temp, intermediate temp, and high temp. The bar trend is accurate. As increasing temperature goes up, molecules are getting into higher and higher energy levels. What shouldn't be happening here is that they're also changing the energy levels, okay? These should be all identical on this y-axis. So this could be 0 to 16, 0 to 16, 0 to 16 every time. I don't know why it's shrinking, okay? Because what it needs to show is when the energy level spacings do not change, but you raise temp, you're still able to get into the higher ones.